So if I want to solve, what's funny, I want to solve some higher order differential equations, but when I actually start solving them, which is in section 4.3, we are in kind of, we're very restricted. We got this, just this special kind of higher order DEs that we can solve, and here's what they are. They're higher order, so they can be third or fourth order. We'll probably start with some theory on second order, but they can go to third or fourth order. But higher order differential equations, they need to be linear. And in section 4.3, they're homogeneous, or sometimes I say homogeneous. I'm not exactly sure what the correct pronunciation is. And they are linear, they're homogeneous, and they have, they're with constant coefficients. So this is funny, man. This is a pretty restricted little batch of differential equations. They gotta be linear, they're homogeneous, and they gotta have constant coefficients. Here's an example of one. Y double prime plus 5y prime plus 4y equals 0. This one's higher order, it's second order. It is linear. If you remember that definition of linear, it was kind of funny, but it is linear. And it's got constant coefficients. The new word, I think, is this homogeneous, and that refers to this right-hand side being equal to 0. So what happens when we ease into the next section, 4.4, all of a sudden 4.4 is what happens when they're non-homogeneous. When they're non-homogeneous, we have a function over here on the right-hand side, and we have a different strategy for those problems. So we'll get to those. But for section 4.3, we're higher order, linear, homogeneous DEs with constant coefficients. We're restricted to this kind of narrow bunch of DEs, but they're good DEs, and you're going to love how you solve them. You're going to love this. Maybe I should give you, well, I'll just tell you how to solve it. You ready? I'll just tell you how to solve it. You write what's called the auxiliary equation. You write what is called the auxiliary equation. That is what they call it. Watch this. You write what's called the auxiliary equation. You turn this differential equation into an algebra equation. Watch. The y double prime, I'm going to call m squared. M is just a temporary variable. The 5y prime, I'm going to call 5m. Maybe you can already guess. If I had a y triple prime, what would I call it? An m cubed. Right. So it's funny. I'm turning the differential equation into a polynomial, actually, an algebraic polynomial. The 4y is just a 4. So this is awesome. You turn it into an algebraic polynomial, and then you try to find the roots of this polynomial. So I told you you're going to love this section. It's very algebraic. You want to find the roots of this polynomial. Okay. I've been doing algebra ever since second grade. Not really. But this factors very nicely. M plus 4, I think. M plus 1. You know, sometimes they don't factor, you know. I mean, I don't really need to teach you algebra, but I'll probably remind you of plenty of algebra. We're done. We found the roots of this equation. The answers, the roots, the solutions, whatever you want to call them. They are m equals -4 and m equals -1. Do you agree? Okay. So, when you find the roots of your equation, now we got a lot of scenarios to think about. Sometimes you can have distinct real roots. That means two different real roots. Sometimes you can have a root that's repeated, a repeated root with a multiplicity of 2 or 3, you know, a repeated root. Sometimes you can have an answer more than once, the same answer more than once. You could also have imaginary roots, complex numbers or imaginary roots. So we have a lot of scenarios to chase down, but the first example is 2 real roots. We found 2 real roots, and here's how you write your answer. You ready? Well, maybe you remember from yesterday or the other day that this second order DE probably has 2 solutions that work. One of them is this, though. They're based on these roots. So one of them is e to the negative 4x. And that's from that negative 4 root. The other one is y2. It's e to the negative 1x, because that's from that negative 1 root. Those are the 2 solutions. But from the other day, you probably remember I can write the general solution as a linear combination of these solutions. The general solution is, and so I rarely take the time to stop and write those 2, because here they come. The general solution is C1 e to the negative 4x, and then C2 e to the negative x. That's the solution. We just solved a higher order DE. Pretty easy, huh? I told you you're going to love this. No crazy integration. No, it's just an algebra problem. It's weird. Again, what I should do is explain to you why this works. Instead, I started with an example. Let's do an explanation of why it works. But the key to making it work, though, is these restrictive rules. I mean, the key is having these constant coefficients is what makes this kind of such a nice problem. But that's what all these are in 4-3. They all have constant coefficients. I mean, this is our game. So watch this. In general, what I'm suggesting is you have an a y double prime, a b y prime, and a c y equals 0, maybe. You know, so now I'm just going to talk in general. And since those are constants, a, b, and c, and somehow it adds up to 0. Now listen, you guys are smart. What kind of function, you know, and you know DE, I'm looking for the function that satisfies this equation. I'm looking for the function y that satisfies this equation. What kind of function do you think you can add?
Exponential?
Yeah, I mean, what kind of function whose derivatives are similar enough that you would be able to add this stuff up and get 0?
Exponential.
It would.
It's in the same form as that, so that's what I'll.
Well, right. You already saw an answer, so maybe you know the answer. But I'm suggesting, right, pretend you didn't see the answer. I mean, what kind of function can you take derivatives of itself, and then the derivatives look like itself enough so when you add them together, you can get
Common
0. I mean, I'm trying to get 0. I mean, if my function was an x squared, you see how no way that would work, right? The first derivative is an x. The function's an x squared. The derivative is an x. The other derivative is a number. Are those going to add up to be 0? Maybe a sine or a cosine does work sometimes in here, but no. What we say is based on the fact that these are constants and that these things have to add up to be 0, we make the assumption, we assume that the answer takes the form, of some e to the mt. We do. We make this assumption. Maybe I didn't do a great job of convincing you that that's our assumption, but what was my convincing? I was trying to say, what kind of function do you take his own derivatives are similar enough, like term enough, to add them together and get a 0? And I think that's the answer, this function. So now check this out. What would y prime be? Y prime, please, for this general. I'm assuming that this is the answer.
y m e to the mt.
He would spit out an m, and it would be m e to the mt. Good. What about y double prime? What would that be?
M squared e to the mt.
m squared e to the mt. Okay, so if I plug those in, I get a m squared e to the mt, bm e to the mt, and c e to the mt equal to 0. If I factor out the e to the mt, I'm left with am squared plus bm plus c equals 0. When does this equal 0? It equals 0 when the quadratic equals 0. I mean, this e function never equals 0. If you set this equal to 0, the answer is never. So if I'm trying to find out when does this equal 0, it's all about finding the roots of this polynomial. So this equals 0 when am squared plus bm plus c equals 0. And when I find these roots, I'm just, you know, again, you could do the quadratic formula to find these roots. But that would just be me writing down the quadratic formula. I'm just going to say that the solutions are maybe an m1 and an m2. Those are my solutions. And then if those are my solutions, the roots of this equation, then I got my two solutions. And I put it together to form this general solution. You guys all right? I mean, maybe you didn't need this convincing. Maybe it helps. I don't know. This is in the book. They run through this. This is the theory of why you address these problems like this. The answer is turn it into a polynomial, find the roots, and put your answers like this. Now, there's a little more to it, I think. Let's try another one. This is classic. Watch this guy. 2y triple prime minus hang on. 2y triple prime minus 7y prime equals 0. See, there's one. Higher order DE, higher order linear DE with constant coefficients. And also homogeneous equals 0. Linear DE, third order this time. It's higher order. So how do you solve it?
Auxiliary equation.
You write the auxiliary equation. You turn it into an algebra problem. You turn it into 2m cubed minus 7m equals 0. And you proceed to do algebra. You guys may need some help with this. I mean, I don't know. We're going to be finding roots of polynomials. We may need our graphing calculator at times can help me find roots of polynomials. Synthetic division sometimes helps me find roots of polynomials. The quadratic formula. But just plain old basic factoring should help me find the roots of a lot of polynomials. So what would you do? Factor out an m. And you're left with 2m squared minus 7 equals 0. Yeah, I would say that one of my answers is m equals 0. That's one of the roots. To get the other two, they're not that pretty, but they're okay. I would set this factor equal to 0, and what would you do? Move
the 7 over.
Thank you, right. Move the 7 over, divide by 2, take the square root. So these are kind of nasty, but I'm doing all those steps in my head. I'm getting plus or minus the square root of 7/2. Okay, I'll just take that like that. Is that what I did? Move the 7 over, divide by 2, take the square root. Cool. By the way, it was third order. It turned into a third degree polynomial, and we do get 3 roots. That's kind of what you expect. Although there are times when you have that repeated root situation. But we do. We got 3 roots. Okay, I'm ready to write my answer. How do I write my answer? Those are 3 different real roots. I'm ready to write y equals c1 e to the e to the 0t. Or I often fall into, I use t. You can use t or x. You know, in the original DE, is it t or x? can't really tell. The independent variable t or x is not there anywhere. But right, y is either a function of t or a function of x. When we do word problems, we use t a lot. I'm kind of in the habit of saying e to the 0 t. C2 e to the square root of 7/2 t. And then C3 e to the negative square root of 7/2 t. You guys okay? That is it. Of course, this first little guy is kind of funny. Nobody's going to write this for too long. E to the 0t is actually just a 1. So it's interesting when you, this is just a C1. That's it. We're done. Problem over. Okay. You know, when we, all three of these, we got these three answers. I mean, here they are. E to the 0t, e to the whatever, e to the whatever. They're all different. What do I mean by that? Our big discussion Tuesday was this long discussion about these solutions, these little functions, this little y1, y2, y3. They got to be linearly independent for us to form this general solution. We never have dependency. We don't have terms that are dependent on one another. They're always linearly independent. So we had a long discussion about whether a set of functions was dependent or independent. Part of the reason was because when we set up these solutions, they should be all independent, and they are. They're different functions. They are linearly independent. I'm not going to prove it to you. But that comes up when we explore this scenario. Here, let's do another one. Here we go, another one. Here, this is classic. Y double prime minus 6y prime plus 9y equals 0. It's a DE, constant coefficients, linear, second order, homogeneous. You simply find the auxiliary equation and find the roots. It's real easy. M squared minus 6m plus 9 equals 0. That factors very easily into m minus 3, and m minus 3 equals 0. Or somebody might have said m minus 3 squared equals 0. Either way, what are you getting here? You're getting one root, but it's a repeated root. You're getting one answer twice, right? The answer is m equals 3. It's a real root, but it is, I'm going to call it a real repeated root. In algebra, the phrase is, it's a solution that has multiplicity 2, because it's an answer twice. Multiplicity 2, because it's an answer twice. Well, that's it. Okay, how do I write my answer? Y equals, logically, from what you've learned so far, you would write C1 e to the 3x. I'm sorry, I went to x this time. C2 e to the 3x. Now, hold on, don't write this. Logically, you might think to write this, but wait a minute. Those are really the same term. In other words, they're linearly dependent on each other. I need two independent terms. So here's what we do. When it's a repeated root, the rules are to make this second one independent from the first one, we multiply by an extra x.
Great.
Well, sure, that's a little out of the blue. But you guys are good at following rules, right? Good. Follow this damn rule. I can give you an explanation of some sort. My original explanation is we got to make it independent. That makes sense, right? They need to be independent terms. And so when we have a repeated root, we handle it kind of special. We tack on this extra x. Hey, what do you think would have happened if this would have had multiplicity 3? Like if it was a root, I would have had another one of these, a C3, and how would I have made him independent? You're right, I would have added an extra x on him. You're right. And now all three of them are independent. I'm going to get rid of him, though. It wasn't part of this problem, but. So you'll just believe the rule and do it, right? Is that what you'll do?
Yep.
Good. You're a bunch of conformists. No rebellion. No. I want to know why first, or I'm not going to do it. You're not going to whine like that, or anything? Yes.
But like adding the x, it doesn't mess up when you get back into the original equation.
Right, it works.
It works.
It's a solution. It's interesting. Yeah. He works, kind of by himself. He works, and by himself he works, and then together the general solution works. It does. Listen, here's an explanation for why we do this, just a sort of an explanation. In the previous class, we did this section 4.2, which was kind of a pain. But if you remember what 4.2 was we would give you a DE. We didn't know how to solve it yet. We didn't know about this stuff yet. We would give you a DE, and we would give you one of the solutions. So I would tell you that this is one of the solutions. And then I would say, find the other one. This in 4.2. I did one terrible long problem like this. It was called reduction of order. Given one solution, can you find the other? Well, now, anyway, I'm not a real big fan of 4.2 because you get to 4.3, you know how to solve DEs, okay? So you solve DEs. So why do you do this thing where you given one, can you find the other? Well, it does help prove this concept. If you're given this one and you went through the method in 4.2 was you assume that this guy is different because he's got to be linearly independent. So you assume he's some function of x times e to the 3x. And then you run through this long procedure to find this u. We did it the other day. Anyway, if you did it to this particular example, what would that u turn out to be? The u would turn out to be the second solution. What would it be? It would be an x. The u, the function, this would be an x. If you went through the damn long procedure.
So we're just skipping that whole...
Yeah, well, I don't need to, right? When I'm up in 4.3, I'm teaching you how to solve DEs. And the rules for handling a repeated root, are here. The explanation for why do you get to tack on an extra little x, the explanation is kind of back here in 4.2. If you wanted to go do this, you could prove to yourself that this is going to be an x. But you'd have to go through the procedure of 4.2, which I'd rather not do again. It would, if you're worried, how do you get to tackle, how do you get to just multiply by a damn x? That would explain it to you. All right, we're learning some stuff. Watch this one. Y to the fourth, and that's, by the way, that's not y to the fourth. It's not y to the fourth power. It's the fourth derivative of y. Minus 9y double prime equals 0. All right, what do you want to do? Write the auxiliary equation. Turns it into algebra. Here it is. It's nice, easy algebra. Look at it. See it? Nice, easy algebra. Now what?
Factor out an m squared.
Factor out an m squared. Then you're left with m squared minus 9. You get your roots. If I set this equal to 0, I get, what do I get?
Are there two m's that equal 0?
Yeah, good job. I get a 0 from this, but it's really 2. This is a 0, this is a repeated 0, thank you. Or a 0 with a multiplicity of 2, it sure is. It sure is. And then what else do I get?
Plus minus 3?
My plus and minus 3, you're exactly right. Again, see, they should add up to, again, a 4th order DE turns into a 4th degree polynomial. And we should have 4 roots. Now, you might look at this and say we got 3 roots, and you're right. But when you count multiplicities, or you count the repeatedness of them, it should add up to 4. We should end up with 4. So 2 of these and 2 of those adds up to 4. Yeah. So how do we write this?
So
The answer is
y equals c1 is c2x.
good. C1 e to the 0x, and then C2 x e to the 0x, and those e to the 0x's are just 1s, so I'm not writing those. Good job. And then C3 e to the 3x, and C4 e to the negative 3x. Yeah. Hey, by the way, anytime we want, we can add some initial conditions to these problems. On a problem like this, somebody would give you 4 initial conditions. Holy shamoly, they would. And you'd have to use those 4 initial conditions to try to find your C1, C2, C3, C4. And you might have to set up a hell of a 4x4 matrix or something. I mean, it depends. It might be easier than that, but right. It could. The initial condition part of this might be the hard part because this was pretty easy. Well, I've avoided this last one. Let's do this one. Y double prime plus y prime plus y. I think this might work. Yeah, this might work. All right, on your mark, get set, go. Right there's the other equation. M squared plus M plus 1. You know, when you're writing this, so far so good, you guys. Anyway, a common mistake is to refer to the y as an m. That's bad. The y is the constant term. The y prime is the m. The y double prime is the m squared. I mean, when they're all in order like this, it's okay. You usually are okay, but there are times when, I don't know, you see the y and you write down m, you make a mistake. That's bad. Here we go. Listen, this one doesn't factor. I think I need the quadratic formula, and it's negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. Yeah, this is the square root of negative 3 all over 2. These are imaginary answers. You know, all through calculus, when you get imaginary answers, you sort of bail out. In calculus, you're working in the real number system. But in this class, and we can use these. We can put these to use. When we get imaginary solutions, I'll have to teach you how to deal with this. Let's see. Let's finish this, though. I'm sorry. This is let's see. How do you kind of pull out an I? Is that I square root of 3, right? And you know, to tell you the truth, when you have imaginary answers, I'm going to do this. You kind of like to have the real part and the imaginary part separate. So I'm going to put this over 2 and this over 2. I mean, I know they got a common denominator of 2, but I'm writing it like that because that's how complex numbers are written, as an a plus or minus bi sometimes. The real part and the imaginary part separate. Well, guess what? How do you write your answers when you have imaginary roots? I guess I'll just tell you. If you have alpha plus or minus beta I, this is how the notes are. When you have complex roots, alpha plus or minus beta I, we write our answer like this. C1 e to the alpha t cosine beta t plus C2 e to the alpha t sine beta t. It's almost like you don't worry about the plus and the minus. The focus is on the alpha and the beta. You know, these are two roots, two imaginary roots, two complex roots, and we wrote two solutions. But they both use the alpha and the beta. I mean, and the plus and the minus was insignificant in a way, except they always come as pairs. When you have imaginary roots, they come as a conjugate pair. They come like that. And you write your answer like that, although a lot of times you could pull out that e to the, you could factor that e to the alpha t out and write it like this. Probably do that. That's pretty wild though, isn't it? The imaginary roots lead to these answers. There's a good explanation for that. There's an interesting explanation for that. It involves this famous Eulers Formula. Have you, I mean, this is, some people call this the most famous formula in math. Eulers Formula is that e to the...
MC squared?
No. All right. That e to the I theta can be written as cos theta plus I sine theta. All right, hold on a second. Let's do this. Let's take a, let's have a little quick discussion on complex numbers. Check this out. Check this out. Here's a complex number. 2 minus 2i. Okay, that's a complex number. Or I'm going to change it. I'm going to change it to -2 plus 2i. -2 plus 2i. This is a complex number. I don't know if you've ever done this, but you can graph a complex number in what we call the complex plane. This is the complex plane. The complex plane has a real axis and it has an imaginary axis. And the real part of this number is -2, so you come over here -2 on the real axis. The imaginary part of this number is the +2, so you go up 2 on the y-axis, but it's the imaginary axis. And that dot, that point, is a picture of this number in the complex plane. Did you ever do that? Maybe. I mean, you know, sometimes this little subject here is addressed at the end of a trig class, because what we do then is when we talk about how a complex number can live in the complex plane, then we talk about how we can write a complex number in trig form. You know, almost like a vector, but it is really kind of just a point. It's not a vector, but what is the angle that takes me over there? And what is the distance that you walk out there? Let's see, if this is over 2 and up 2, what is that hypotenuse? That hypotenuse is 2 square roots of 2, using a little Pythagorean theorem, over 2 and up 2, that distance would be 2 square roots of 2. And do you know that angle? If it's over 2 and up 2, that's a 45-degree angle. In quadrant 2, that's a 135, or I'm going to call it 3 pi over 4 is the angle. And so I can write this trig function like, I can write this complex number in trig form like this. The hypotenuse is sort of out front, multiplied by the cos of the angle plus I times the sine of the angle. complex number with a real part and an imaginary part can be written in trig form. But then what's really amazing is it can also be written in this thing called exponential form. According to Eulers Formula, this is true. So anything that's in trig form can be written in Eulers form, and in higher and advanced mathematics, this is how you write complex numbers. This complex number would be written as this number out front, which I didn't show you in this formula, but this number out front, e to the I theta, 3 pi over 4. I mean, this is this complex number, it's this number. So it's exponential form for complex numbers, trig form for complex numbers, standard form for complex numbers, x's and y's. This is x and y form, I guess.
Linear complex.
Okay, so I don't know. We don't need all this information. I thought it was interesting. I thought you would like it. At some point in some higher math classes, or you might see people talk about imaginary numbers in these forms. Anyway, we kind of needed it, though, to prove to you, why do we write these roots like this? Well, maybe you can see why, but I'll help you see why. In other words, let me try to pretend I was just doing a DE, and I got these two roots. All right, those are my two roots. And if I didn't know about this rule here, I want to try to derive this rule. So from what I taught you earlier, if those are your roots, you write your answer like this: C1 e to the alpha plus beta I t, and then C2 e to the alpha minus beta I t. I mean, isn't that what I taught you to do with two roots? Well, two real roots, that's what you did. And the truth is, you can do it with these, except this leads to that. This will lead to this, kind of through this formula. And you can kind of watch it happen. You can do it yourself, but I'll help me do it. You ready? Here we go. What can I do here? Oh, one thing I can do is kind of distribute the t. Yeah, hang on. I can do C1, I can write e to the alpha t. You know, can I write this, watch this, times e to the beta I t? Because if you were multiplying these bases, wouldn't you add exponents and get that? Okay, so now let's move over here. C2 e to the alpha t times e to the negative beta I t. All right. All right, so now I'll factor out that e to the alpha t. I'm going to factor out that e to the alpha t. And I'm left with C1. Now watch this. I'm left with this, right? This e to the beta I t. According to this formula, e to the beta I t. Hang on. E to the beta I t. Who is my theta? What's my there's my I, there's my I. Who's my theta? BT or beta T, I get where you, yeah. So my angle is beta T. So I'm about to write, what am I going to write? E to the I theta is cos theta plus I sine theta. If my angle theta is beta T, I'm about to write cos beta T plus I sine beta T. Is that what I'm doing? According to Euler's formula. Okay, plus C2. And now what am I going to do on this one? Okay, remember, this guy's factored out. And now I have this. So who is my theta? Negative beta t. So I'm going to write cosine negative beta t plus I sine, I'm going off the page here, plus I sine negative beta t. You guys okay? So now what? I can sort of distribute. Let me try to collect, like, oh, I know what it is.
You can cancel.
Well, there's this old identity. You know, the cosine of a negative angle is the same as the cosine of the positive angle. That's a true fact, always. Cosine sort of absorbs the negative sign, you can kind of say, on an angle. That's always true. And for sine, it's this. The sine of a negative angle is the negative of the sine of the angle. So the negative sign kind of passes through the sine function like that. Those are true identities. You could walk around a unit circle and convince yourself of those someday. But how am I going to use those? Oh, so this negative sign just is going to get absorbed here. So that cosine beta t is the same as this cosine beta t. So let's just add them up. What are their coefficients? Well, it's a C1 and a C2. Can I just add those together and call them C1? Okay, so I hope I'm not losing you. I guess I'm sort of distributing this C1, and then I decided using that identity that this is just cosine beta t, and I can add it up with this C1 cos beta t, C2 cos beta t, add them together, but let's call their coefficient C1. It's a C1 plus a C2, but let's call it C1. All right, you're convinced. Thank you. All I need is a nod, one little nod, and I'm off to the races. But that makes sense. All right, what about, here's the funny part about this proof. Somebody should, I mean, somewhere right here, the proof we're about to prove this, but it gets fuzzy right here, and I never know if I don't think I ever have figured this out. Maybe I have one day, but I forgot. There's this little fuzzy part is this. Now I'm going to add up these signs. Now wait a minute. Oh wait, what are you going to do with this negative beta? To get the negative sign, you'll just pull it out, won't you? All right, so you're going to have C1I sine beta t. And then you're going to have plus this guy. What's this guy going to be? C2I. Minus. Oh, but he's going to be minus because we're taking the minus sign out. He's going to be minus C2I sine beta t. And then this is the part I get a little confused about. But we join that together and we call it C2 sine beta t. And the proof is over. But that got a little fuzzy there, didn't it? Yeah. What's fuzzy? What is fuzzy? What are you... A second ago, I had a C1 and a C2, and you let me call it C1. That wasn't fuzzy, right? A C1 and a C2 is a C1. This is a new, call it C3, it might be better, but then change it to a 1. I mean, you were convinced about that. But what's funny about this is that constant and that constant, I mean, maybe I is considered a constant, but I add up those constants and I call it C2 and I lose the I. And I don't have, the I doesn't show up and I'm not sure what, that's the fuzzy part. If you research the fuzzy part and get it unfuzzy, you can earn an extra 1,000 points this semester. Not really. but you might just satisfy your own curiosity, which is worth 1,000 fake points in your head. Okay. Like Mario's gold coins or something, you can, whatever. You with me? That's a little fuzzy. I mean, the book proves it. The book has an explanation. I think I've read it 6,000 times. I'm not sure if I ever understood it. Oh, they might need to use Maclaurin's series. Huh. Yeah. Wow. I don't know. That I sort of disappears and gets absorbed into that constant somehow. I don't have a good explanation for you. Sorry. Maybe we should have stopped the video.
Wasn't the I considered a constant?
Well, I is not a variable. I mean, it is a constant. It is the square root of -1.
So if you were to distribute like the C2 and like the C1 into that function, would the I just get absorbed by the C1 and C2?
I mean, maybe if you want to call I just a constant. I mean, I kind of get your point because it sort of is, but it is an imaginary constant. I mean, I'm thinking these other guys are real, and in the end, when you do these problems, these C1s and C2s, I mean, here we're at the end here. This is our answer, like I said here. The C1s and C2s, when you have initial conditions and you go find they're never imaginary. They are real numbers, so they don't. The C2 doesn't come out imaginary. It is real in the end. So anyway. That was pretty good proof. And that was a decent discussion. But now, you got it. You got all the rules. How do you handle real roots? How do you handle real repeated roots? How do you handle complex roots? Right? You got all the rules. And you can have, I guess you could have complex roots repeated. That kind of sucks, but it could happen, but I won't ever let me do it. But yeah, you got everything now. Let's try something else. What about let's try another DE here. Y, this is classic. Y double prime minus 4y equals 0. No, plus 4y equals 0. Okay, so yeah, this is classic DE. So what do? Write your auxiliary equation. What's your auxiliary equation?
Squared plus 4.
M squared plus 4 equals 0. Okay, you try to find your roots. Your roots are, move the 4 over. It's a -4. When you move it over, your roots are plus or minus 2i. Excuse me, yes, plus or minus 2i. All right, we're done. I think we should be able to write our answer. You know, the one little thing you should recall, though, is these complex roots are an alpha plus or minus a beta I. In my example, I need to maybe think of that as a 0 plus or minus 2i. The focus is on the 0 and the 2. I mean, that's your alpha and beta. And where do they go? They go, you know, right there. So, so the answer is y equals e to the 0t. What am I going to write for e to the 0t? 1. And then it's a c1 cosine 2t from the 2. And then a c2 sine 2t. That's it. And that's just beautiful. That's a beautiful sine or cosine wave. I mean, that's just a nice wave, is what that is. You know, with a certain period and yada yada. Yeah, that's classic. That happens a lot. We get these imaginary numbers, imaginary roots with the real part being 0. But not always. We can have it. We can have an alpha. Well, that went pretty fast. You know, I feel like easing into 4-4. I mean, I could try millions more examples of these. Maybe I should. Hang on just a second. Don't look. I hope I did that right. All right. There's a DE. Constant coefficients, linear, higher order, constant coefficients, DE, homogeneous. We write the auxiliary equation. What's the auxiliary equation? Yeah, I hope I did that right. All right. So now what? I mean, now we're back to. I mean, it, kind of maybe the toughest algebra you ever did was. I mean, when you have polynomials, it's hard to find the roots of a polynomial. I mean, it's hard to factor third degree, fourth degree polynomials. I mean, I think the thing that helps me factor third or fourth degree polynomials is synthetic division. I mean, I used to, and if you remember, synthetic division was always just, okay, start guessing. I mean, you really, you didn't have, there was some rules about it, what to guess and what not to guess, but you would really just start guessing. Usually it would be factors of this number. So maybe you guess 1s and 2s and 4s and 8s, and but plus and minus 1s and, I mean, or what I saw was a bunch of people pick up their graphing calculator. I mean, if you sketch a graph of this polynomial and look for when it equals 0, maybe you see a root.
2. Just 2.
Oh, now you saw 2? You saw 2 on your graphing calculator? Did you see 2 on your graphing calculator?
No, I just.
You just saw 2 in your brain.
Yeah.
You saw it on your graphing calculator. But somebody he just saw it too. He just said, you just saw it too. It's pretty. Good vision. That's like X-ray vision. 2. Anyway, I think 2 is a root. I think you're right. Now, what are the other ones? I don't know. See, so you know what? Even though you know 2 might be a root and you saw it on your graphing calculator, or the synthetic division is still kind of a valuable tool. If you recall, if 2 is a root, let's try it. I'm gonna do synthetic division. The coefficients are 1, 2, 0, and negative 16. You got to remember that 0. That's important. Synthetic division used to work like this. You would pull down the 1, multiply, put it here, add. Multiply, put it here, add. Multiply, put it here, and add. That's your remainder, and if you get a remainder of 0, woo-hoo. It worked. You found a root. You found a solution. You found a root. So we know that m equals 2 is one real root. But what's more important, actually, maybe, or whatever, is that what's left here is your remaining quadratic factor. This was a cubic polynomial, and after you have a successful synthetic division, what remains here is a quadratic factor. And you can solve any quadratic if you can solve any quadratic because you can do the quadratic formula, right? So if you can, so those cubics are kind of a pain, but if you can find one root to the cubic, then you're down to a quadratic, and hopefully you can get the other 2. But you might need these skills, these graphing calculator skills or synthetic division skills to find that first root of a cubic polynomial. I think I'll do the quadratic formula as fast as I can. On your mark, get set, go. Negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. Okay, thank you. That's negative 4 plus or minus, that's 16 minus 32. That's the square root of negative 16. That's 4i. That's awesome. All over 2. Oh, that is beautiful. This is a negative 2 plus or minus 2i, isn't it? Is that what you guys got?
Yeah.
Good. So I think I'm ready to write my answer. Let me think. This was a third order DE. It was a cubic polynomial, and I believe I got 3 roots. I got 1 real root and these 2 complex conjugate roots. So I got my 3 roots.
Y equals C1.
Y equals C1 e to the 2t. That's how we handle the 2. And then the complex roots you handle by, let's see, e to the negative 2t times C1, well, I better not call it C1,
C2.
C2 cos 2t plus C3 sine 2t. That was my, well, I erased my rules. That was my e to the alpha t cos beta t sine beta t. Both, you handle the pair of complex roots kind of in one blow there, right? You handle the pair of in one blow. Cool, that's my solution to this, Dee. General solution. All right, I got a little time to discuss. I might move into 4-4. I'll give you a little preview here. 4-4 is all of a sudden it gets a lot tougher. I'm sorry, because all of a sudden we're in the same game, but now they're non-homogeneous. And I'm just going to make one up here. Y double prime plus Y prime equals hang on a second.
Six would be nice.
Okay. E to the, I'm sorry, 3 e to the 2t. All right, so what's new? Well, what's new all of a sudden is it's non-homogeneous, which means this right-hand side has a function. It'll be a function of t's or x's. I guess I keep using t's lately. And the general solution, when they're non-homogeneous, these are your kind of your notes. The general solution, y, is this. It's made up of a y subscript c plus a y subscript p. This y subscript c is called a complementary function, I think. It's the, let me tell you what it is. It's the old general solution. It's the old general solution to the homogeneous version of this DE. The YC is the old general solution to the homogeneous version of this DE. You probably know what I mean by that. That's clear. So you pretend it's homogeneous and you solve it like we've just been doing for the last hour. Right, and that's that. But because of the right-hand side, because of this non-homogeneous part, that generates another piece of the solution called YP. YP is I'm going to call it a particular solution. It doesn't have any C's in it, by the way. It doesn't have any C1s and C2s and stuff in it. It's a particular solution, and I'm going to say this, we obtain it by guessing.
Great.
We're guessing, I'm going to write this, these are my notes, guessing this, that it takes the form of the right-hand side. The right-hand side. All right, those are my notes. We got to do a problem. So the final answer is made up of a YC and a YP. And let's work on that. So how do you get the YC? Well, you get the YC by, just for a brief second, pretending this is homogeneous. Pretend it equals 0. What do you do when it equals 0? Oh, you find your auxiliary equation. and you get your roots and write your answer, right? You guys okay? I'm going to factor out an m, I think, this time. And what are my roots? M equals 0, m equals -1. You guys agree? So I think my my YC is C1 e to the 0t, which I won't write, C1 e to the 0t, plus C2 e to the -t. All right, that's the good old YC, the good old solution to the homogeneous version of this DE. Okay, so what's the YP? The YP is a particular solution, and we obtain it by guessing that it takes the form of the right-hand side. The game is, if this right-hand side is this exponential function e to the 2t with some number multiplied by it, my guess for the YP is some unknown coefficient times e to the 2t. Now, in a way, that's a general guess, although there's a specific part to the guess. The specific part is that it's an e to the 2t. It's not an e to the bt or an e to the 8. It's an e to the 2t is specific, but the coefficient in front is an unknown a. That's and the skill of guessing the appropriate YP takes a little practice. I mean, this is one example. We'll do more of this next week. But the skill of making the appropriate guess right here takes a little practice. The book guides you through it. I'll guide you through it. But for now, this is your guide. We guess something that looks like that. Okay. Well, then what we're suggesting is that he's a solution. If he's a solution, what does that mean? You can take his derivative, and you can take his second derivative, and you can plug it in. If you plug it in, what you'll be doing then is you'll be working with this unknown a, and then you'll plug it in, you'll equate things on both sides of the, and you'll find a. It's sort of, the method is, you're looking for these undetermined coefficients. Here, let's try it. I take the derivative. What's y prime of p? 2a, yeah, e to the 2t. It's pretty easy. And then y double prime of p? 4a, e to the 2t. And then here's what I'm saying. We actually plug these in. That's a y double prime. So there's y double prime. Okay, I plug that in. 4a e to the 2t plus this y prime, which is 2a e to the 2t. And it should equal the other side, which is a 3 e to the 2t. And it's not too hard to figure out what a is it? It turns out the e to the 2t's can actually be divided away if you want to. I mean, what I'm interested in is the coefficients. This is a 4, this is a 6a, and the 6a should add up to equal 3. So a is 1/2. And we found a particular solution. Our YP is, we got it. Our YP is specifically now 1/2 e to the 2t. It takes on the form of what's there, but it's not, it's generalized and well, it starts generalized, and then we find the a that makes it work. I probably should try another example. I got 7 minutes. But hold on. At the end, you're supposed to find YC and YP, circling them and saying, that's my answer is a little, you should write your answer. And your answer is Y, which equals
C1 plus
him plus him. Right. So it has this general thing, and then it has this specific, particular piece. Yeah, there it is. There's the general solution. Let me try another one real quick. Watch this one. another one. You guys okay? All right. We'll do one more here. Step 1. Pretend it's homogeneous. Pretend it's homogeneous. Pretend you have an auxiliary equation that equals 0. Just pretend it equals 0. And get your auxiliary equation. Did I do that right? And get your roots. And what are the roots? Plus and minus 3. And you can write your YC. Your YC is C1 e to the 3t and C2 or x. I'm sorry, I should use x this time, I suppose. Everybody okay? That's pretty easy. Okay, so now I have to make a guess for my YP. And what I've said is that my guess it takes on the form of what's over there on the right-hand side, but you generalize a big chunk of it. So my guess for YP is going to be a generalized cubic equation.
X cubed plus b.
Well, more bx squared, cx, and d. I mean, some of those terms might not exist, but I have to. I have to guess like this. Again, the little rules of guessing will take a little work to figure them all out, but there's a nice guideline in the book, though. In section 4.4, there's a nice kind of guideline for guessing your YP. But we'll practice more and we'll get better at it. But that's it. So now what? If you remember, you make this general guess, and then you take derivatives and use those derivatives by plugging them in there, and then that helps you find your unknown coefficients, A, B, C, and D. I mean, I need, I don't really need y prime, I guess, but I need y prime to get to y double prime. So I need y prime. Y prime. 3a x squared, 2bx, and plus c. You guys okay? And then y double prime. 6ax plus 2b. And then we actually plug these in. Here, I'm going to show you how to do this. I need a little more space here. Sometimes I like to do some of this in my head so I don't have to do so much writing, but I'll write down a few things right now. So what I'm plugging in is y double prime, which is 6ax plus 2b. Be careful here. And then it's minus 9 times y. And where's y? Oh, yeah, that's the original y right there. If you don't mind, I'll distribute my little 9 through there as I do this. I'm going to call that minus 9a x cubed minus 9b x squared minus 9cx and minus 9d. And that should all equal the other side, the actual right-hand side, which is 4x cubed plus 8. You guys, the game is, and we've played this game in another context. We sometimes, I don't know, back in partial fraction decomposition, sometimes you would play this game where you equate coefficients of like terms to find the unknown a, b, c's, and d's. So like, look for all the x cubes over here. See all the x cubes over there? How many x cubes do I have on the right-hand side? 4. How many x cubes do I have over here? Negative 9a. Well, then the coefficient of the x cubed should equal the coefficient of the x cubed over there, and cool. I can find a. I'm equating coefficients of like terms is what I'm doing. Divide by negative 9, and we found a. There's a. Circle it. Hang on to it. What else could I do? That was looking at the x cubes. Maybe I can be a little more organized here. You want to look at the x squareds? Let's look at the x squareds. Ready? Over here on the left-hand side, where's all the x squareds?
0.
Oh, well, no, there they are.
Oh,
Negative 9b. But now over on the other side, how many x squareds do you have? 0. Well, then very quickly you realize that B is 0. Okay. All right, let's look for all the x's. Let's look for all the x's. All the x's. Over on this side, please. 6a minus 9c. 6a minus 9c. Now that should add up to equal all the x's over on the other side, which is 0. But now this time, see, a second ago, that meant that b was 0. This time, we're going to find something here, I guess. If a is negative 4/9, I'll plug that in. And I'll move it to the other side. It's a negative 24/9. I move it over. It's positive 24/9. I divide by a negative 9. C is 24/81. Negative 24/81. Beautiful number. It reduces a little bit. If you divide by 3, it's a negative 8/27. That's a little better. That's my C. You guys okay? It's kind of a tedious method. It's not necessarily that difficult, but a little tedious. What else should I look at? I looked at my x cubes, my x squares. I looked at my x's. What else? Anything else? Oh, numbers. Yeah, plain old constants, or I'm going to call them a number. Right, we should look at those guys. Well, who's all the plain old numbers? Oh, here they are. 2b minus 9d. Yeah, 2b minus 9d, and that should add up to equal 8. Oh, good, and we already know that b is 0. So that helps. b is a 0. This term is 0. Negative 9d equals 8. Divide by negative 9d is negative 8/9. Wow. So can you write your yp? Good God.
Can we just write the answer now?
Well, okay, we can write our answer. Our answer is y equals the yc. What's the yc? It's right above me. Here it is, right above me. The yc plus the yp. And the yp is right here with that a, b, c, and d filled in. Negative 4/9 x cubed. 0x squared, that's pretty sweet. 0x squared. Negative 8/27 x. And negative 8/9. Wow, you guys are awesome. We found the solution to this VE. All right, let's quit. Hey, try 4-3, maybe ease into 4-4. I'll help you Tuesday.